Okay. Okay.
We're doing. Oh,
Yeah, honestly, like, we're good? Everybody's okay?
I mean, about Calc in general.
Yeah.
Yeah, that is two different.
Right? Let's do two different things.
Two different answers.
Sure.
Well,
I'm interested in either.
Well, well, I get to leave school at 12:40 every day, so.
okay, but
That's pretty so much.
okay, well, I did well.
All right. Should we talk about our schedule, where we stand here?
Yeah.
All right. So I missed that day last week and kind of threw a monkey wrench into all the plans that we had kind of set up.
I missed it too.
So what do you guys, what's going to be fair? What do you guys want in regards to the test date? Does it need to be moved? That's fine. That's fine. Is that legitimately what we want?
Yeah. Discuss this.
Okay. That's fine. I will ask then, I'm gonna get a section together from chapter 4 for you guys to do on your own. Like I'll make a video or whatever of what's going on, but we do need to like catch up a day in there, so that's going to be my solution. Whether you want to do that as part of the asynchronous time, or if you want to wait till after the test and kind of like cram that through or whatever the night of the test, whatever works for you. But we need to kind of catch a day up in there that and that's not your fault, but I can't like sacrifice a day there and then sacrifice an asynchronous day and then still kind of get through what I wanted to get through this semester. Yeah, it would just be starting the next chapter. Yeah, exactly. So we'll do 3:10 today, right? We'll do questions and whatnot then on Wednesday. Or maybe try to do that for one section on Wednesday, non-test. See what you guys are feeling. And we'll do the test when you guys come back from this little long weekend or whatever. Does that feel okay schedule-wise? That's doable? Okay. 3:10 that we have to do today is not real long, and I don't think super difficult. So we should have some time, even if you wanted to get back together and work on those related rate problems. My hope is we'd have 20 or 30 minutes here at the end that we could do that. Okay? Because I know those are still kind of dangling out there on you guys too.
You want those new ones there?
Yeah, that would be great. If not, like, if you turn them in before the test, I guess I can live with that. But I prefer to have them before then. But it is what it is. Mia, you just hand them to me on a sheet of paper. Would be fine. If they're in OneNote, just print it. Like that's fine. Like whatever. It just felt like it was going to be easier than trying to collect them digitally.
Yeah.
Since it's like the things on the questions are on the screen and then like you're having to toggle back and forth. It felt like a hassle. If you did it digitally, that's fine. Just print it and hand it to me.
One copy per group.
I'd kind of like everybody's to have their own, to be honest with you. I think even if it's like we did this together and this person did all the writing, I think you writing it again is probably helpful. You know what I mean? Just as a exercise in retention or whatever. All right. So let's talk about 3:10 here, which your textbook like really goes out of the way to try to make sound really complicated when it's like tremendously straightforward. So my hope here is that we're going to I'm going to just try to translate some of the language the textbook is using and symbols the textbook is using and just kind of describe what's going on, because the actual process that you'd be using is like a chapter 2 idea. So 3.10 is about linear approximations and differentials. So here's the idea, right? Now let's say we have some goofy function here, right? And we have some point here, we'll call that point A. So that's like the point A comma f of A, right? If we write the tangent line to f of x at that point A, that would look like this, right? And how would we write that equation? Well, that would be like f of A plus the slope at A times x minus A, right? That's just the point slope equation rearranged so that the y is by itself, where I just added the f of A, the y coordinate over. Everybody's okay with that? So if I look at some other point, call this like A1 or something, or yeah, it's fine. Let's actually make that a little bit closer. So let's say that that's our point A1, or another x value A1. So this point here would be like A1 comma f of A1, right? And if I plug that in up here, that would be the point A1 comma, and then we're just plugging A1 in for the x into our tangent line equation. Right? So this equation here is what the textbook is going to call the linearization, or the linear approximation, or the tangent line approximation. All of those are equivalent. So as long as I'm talking about a value that's relatively near A, the tangent line is going to give me a decent approximation of what the function is doing, right? And the closer to A you get, the better that approximation should be. Everybody agree with that? So when we talk about a linear approximation, all you're doing is writing the tangent line and then using that to approximate values. That's all we're talking about. So just writing the equation for the tangent line and then plugging x's into that tangent line to approximate values for the function. Everybody's okay? So this distance here, let's give a name to that. Let me find the right picture for this that I want. All right. Let me actually get a little bit more detail in here first. So let's say the distance from A1 to A, let's call that distance delta x. Now in this picture, since this is a function that depends on x, that delta x is like the same idea as the dx in our dy dx. Everybody's okay with that notion? And when you're doing a linear approximation, the dx and the delta x are going to be the same always. So when we're working in 310, the differential dx is just equal to the change in x, the difference between your two x points that you're approximating. Now, if I think about like a right triangle here, that piece there, again, is the same thing as my delta x or my dx. This piece here is like my delta y. And then this piece here is like my differential dy. So when we talk about this dy, the important thing to remember is that dy dx is equal to f prime of x. So dy is just f prime times dx. And in most cases, that's going to just be the same thing as f prime of x times delta x. Now delta y is just really the change in y coordinates. So that's like f of a1 minus, let's make that, call that a up in there, minus f of a. I guess in our picture, there's really a minus sign there, right? So let's do a couple of examples here, right? So if we ask you to find the linearization of f of x equals the square root of x plus 3 at x equals 1, and then use this to approximate 3.98, or the square root of 3.98 and the square root of 4.05. When we say linearization, what are we looking for? I'm just talking about a tangent line. That's all we're asking you to do. What am I building the tangent line for? This function at that x value. Okay, well, so we'll start by just taking the derivative of f of x. To do that, I'm going to think of f of x as x plus 3 to the 1/2. So I get 1/2 of x plus 3 to the negative 1/2, and then the derivative of the inside is just 1. So now I need two things, right? I need f prime of 1. Which is 1/4. And I need f of 1, which is 2. So I write y minus 2 equals 1/4 times x minus 1. So that's going to be minus 1/4 plus 2. So that would be plus 1.75, or you could call it 7/4. Either one is okay. Oops. Everybody's okay there? So that's my linearization. Now if I want the square root of 3.98, what is that? Well, that's the square root of 0.98 plus 3, right? Sergio?
Quick question. Are you this?
I mean, that's just the same thing as 1.75. I just wanted to iterate that, like, I'll get rid of it if it's confusing. So remember that f of x was the function we're using to do our approximation was the square root of x plus 3, correct? So 3.98 would be 0.98 plus 3. So in this case, it's the x value that we're working with is 0.98. So all I'm going to do now is just plug that into my linear approximation and see what I output. So I get 1.995. Actually, I don't need an approximately. That's just a hard equals. And just for the record, if I wanted to look at how good of an approximation that is, that ain't bad, right? That's pretty good. The other one we wanted to approximate was 405. So that is 1.05 plus 3. So x would be 1.05. What's up?
Oh, wait, no.
So when I do that, I get 2.0125. Is everybody okay with what I did there? Quite easy, right? Not a big deal. All we're doing is writing the equation for tangent line and plugging some values into it. One thing you'd often be interested in with your approximation is, like, for how long is this going to be a decent approximation? So, for example, you might ask, so we might ask, like, for what values of x is our approximation accurate within, like, half a unit or a tenth of a unit or something, right? Like, depending on what you're using it for, that's certainly something you don't want, something that's wildly inaccurate if you're going to use this in a, engineering-ish calculation. You want something that's going to be like, okay, this is easy to compute, and it's going to be good enough, at least for what we can measure. So if I want this accurate, say, within a half of a unit, what does that mean? It means that when I take the actual value and we subtract the approximation, we should be either getting 0.5 or negative 0.5, right? But it's not really equals here, is it? What we want is actually, because it would be okay if it was less than 0.5 or greater than negative 0.5, what we really want is an absolute value there. And we want that number to be less than 0.5, right? Or less than or equal to, depending on the context. Let's just go with a less than here. Everybody's cool with that? Yes.
Why did you decide that it was a less than?
I just picked to be less or equal. It just would be the question. It says within 0.5, so that means like inside of it, not including.
Okay,
If it said like at least,
then you would do.
then I think it would be or equal to. So
Okay.
just like the wording of the question is why
Okay.
it was 0.5 and or less than rather than less than or equal to. Paul?
So wait, what if it doesn't have less than 0.5? That turns out to be false.
That there is nothing?
Yeah.
That could happen.
Okay.
You just state that. Okay, who remembers how to solve a absolute value inequality? Yeah, but what about the inequality symbol? When does it flip? Well, no, when you make the inequalities here, one of them is going to flip. And you either end up with an and inequality or an or inequality. Does anybody remember the rule for that? The one that you make negative, the inequality symbol needs to flip. Yeah. So the one that I made negative, the inequality symbol flipped. Which should make sense, right? I want that difference to be bigger than negative a half and smaller than positive a half, which is what we've written here. That still equates to the same thing that we wanted. So I'm going to write this then as like a compound inequality, just because it's a little bit neater to work with that way. And while I'm at it, I'm just going to distribute that negative sign through. So far, so good? Okay. So what I'm going to do then is, let's see, probably the easiest thing to do here would be I'm going to subtract this square root thingy-majobber from both sides of my inequality. Everybody's okay with that? And then I'm going to divide everything by a negative. What does that also do, though? Flips those inequalities.
Why would you divide by a negative instead of multiply by a negative?
No reason.
Would
They do the same thing.
Would a multiplying by a negative still multiply?
Yes. And really, probably the more natural way of thinking about that would be to write it in the reverse order so that the smaller stuff is on the left and the bigger stuff is on the right. Now, this is just like a matter of style here, but everybody's okay with that? Now, to solve this, what do I need to have true? I need this to be less than, and I need this stuff to be less than. So to solve this, what I want to do is I want to get the square root part by itself. So I'd add 0.5 to both sides. What's 7/4 plus a half? 9/4. And then we'd need to square both sides. Does squaring both sides, is that going to change the direction of my inequality? No, it does not. Good. I saw Robbie shaking his head. So I got to FOIL that piece out. So now I have a quadratic inequality, right? To solve this, we'd have to get this equal to 0. So if I subtract 1x from both sides, that gives me 1/9 x. If I subtract 3 from both sides, that would give me 69/4. Everybody's good with this? And then what do you do now? You got to apply the quadratic formula. Guess what happens here? You get no real solution. But that's okay.
Wait, what? You just go back. That's so much fun. Oh, because. Never mind.
So I applied the quadratic formula, and when I do that, I get no real solution.
Oh, okay.
So that what that's saying is that my linear approximation is never bigger than 0.5 less than the actual, right? I had done it already.
So, but we're gonna need to do that.
That's, yeah, I'm just writing down notes of what I did there. I didn't write down like me plugging things in and showing you get like a negative value under the square root, but like you take my word for it, right? And that's okay though, right? Because, okay, if my approximation is never worse than 0.5 less than, that's good then. We just have to worry about if it's ever too big, right? It's never going to be too small. So we'll do the same thing over here. So here I have to subtract a half. And then we'll square both sides. Make sure I write this down right. And then same idea. So subtract a 1x over, and then subtract a 3 over. Oops. That should not have turned. What's up? It's okay? Okay. If you see typos or mistakes, please, for the love of God, like, say something. I don't mean to do it ever. So again, at that point, we apply the quadratic formula, we get two answers. Now the question is, am I talking about between those two numbers or on either side of those two numbers? Here's how you can tell. It's not bad. So here's like negative 266, and say here's 866. And I'm looking for the part where the quadratic is below the x-axis, or this is like the x-axis. Which way is that parabola going to open? Does that parabola open up or open down?
Down.
Opens up.
Oh,
How can you tell? The leading coefficient is positive.
I see.
So the parabola is going to look like this. When is the parabola below the x-axis? Is it in between those two numbers or outside of those two numbers?
Outside. Oh my God.
It's in between. It's in between. Now, alternatively, could we have done this on the calculator? Sure. So what I would have wanted to graph would have been this piece here. So that's square root x plus 3 minus 0.5. And then 1/4 x plus 7/4. And then square root x plus 3 plus 0.5. But that's a lot of stuff going on. I'm going to just graph the first two. Let's see. Well, I'll probably do that from -10 to +10, going by ones. And then the y's, this was all happening right around, I don't know, whatever, -10 to +10, we can refocus if we need to. So there's my square root function. There's my linear approximation. Notice that my linear approximation is always bigger than the smallest that I want it to be for the error, right? The square root of x plus 3 minus 0.5 is always less than my approximation. So that's good. That tells me that that part is fine. I don't have to worry about it being my approximation ever being too small. Everybody's good? So I'll just turn that one off and then turn on the what happens if it's too big. So there's my linear approximation. There's the square root. So let's go from 0 to, I don't know, 6 or something and get a little bit better picture of that. So again, here's my linear approximation. There's where my square root function, I could just find the intersection of those 2 points, and that would do it for me. That'll be the -2.66 and 8 point whatever, 66. Is that okay?
Yeah, but that one's facing down. That's going like this.
Well, that's not the parabola I solved though, right? This is the parabola I was solving. That one is the one that's facing up. This one is bending the other way, but it's fine. It's okay, in between those two values, right? We're looking for when the approximation is too big. I'm worried about when my approximation is above that square root curve. So that happens before this point and then after that point. In between, though, it's good. It's smaller than the too big part.
And so then when it was the first equation, the linearized one, you know how there was no real solution?
Right.
Is that what showed on the calculator?
Yeah, because it was never below it. Yeah, there's no intersection. It was always oh yeah, that's always going to be bigger than too small, right? So it's okay, good, great. Always bigger than too small. I love it. Is that okay? So again, I did it algebraically because, well, if you run into the AP exam and a no calculator thing, should review how to solve one of these things with the absolute values in there, because and the inequalities is kind of tricky. It's been a long time since you've had to deal with it. But this is something I would just do on my calculator and look at the picture. So what I was doing was I was looking at this part here. So those are the three things that I graphed. And I was just comparing that linearization part. Is it ever below too small? Because like this is the too small line. Is it ever less than that? And this is the too big line. So then I was looking at, was it ever above that? And it was never below the too small line. So I was like, okay, well, that's good. That's one less thing. Does that feel okay? Great. Great. Okay. So let's talk about these differential parts. So compare delta y and dy if y equals f of x equals x cubed plus x squared minus 2x plus 1, and then x changes from 2 to 0.5. So first thing to check or to observe here is that our delta x or dx here in this case is 0.5. So our delta y is just going to be our change in y coordinate. So if you move from f of 2.05 to f of 2, that's going to be my delta y. So that's just, I plug that into my function up here and type that junk into my calculator. What's the fastest way to type that into your calculator? Just as an aside. Mr. Kulik's just putting that into the y equals menu. So we can use the f of command. Right? That's the easiest way to do it. Least chance for a typo there. So there's that. How do I get dy? Well, dy dx is going to be 3x squared plus 2x minus 2. So dy is going to be 3x squared plus 2x minus 2 times dx, right? And when x equals 2, my delta x was 0.05. So this becomes that. Now, what's the easiest way to type that into your calculator? I'm going to do math scroll down to the bottom and pick n derive. So I'm going to do d dx of y1 when x equals 2. And then I'll multiply that all by 0.05. So I get 0.7. Again, just a little bit quicker and easier and less chance of, oops, that was 0.7, not 0.07. Less chance of making a goofer typing buttons into your calculator. So again, your calculator can do derivative at a value, right? It is very effective at doing that. Use that command. Makes life much, much easier. What do you think? So what if we wanted to talk about the error here? Find this real quick. Thinking that, where did you go? There it is. No. So in the homework, they're going to ask a couple of things. They're going to ask for like the max error, and they'll ask about the relative error, and they'll ask about the percent error when we do one of these approximations. So the maximum error, that's just your dy. So our relative error is going to be like the change in y over y. And I know the change in y is about the same thing as dy. My dy was 3x squared plus 2x minus 2 times delta x, or dx, either one is okay. Actually, probably makes more sense to call that dx right there. And then my f of x was x, or my y was x cubed plus 2x squared minus 2x plus 2. And then I just plug in where x equals 2 and, oh, sorry, was it plus 1? Thank you. And dx equals 0.05. So for us, that's just going to be this guy divided by, oops. Y of, or y1 of 2. So 0.077. And percent error is just going to be that relative error times 100. Everybody's okay with that? Okay.
Wait, I have a question.
Yeah.
So, for relative error, when y is equal to 2, so we're dividing basically we got 0.7 for dy, and for y, are we just plugging in 2 for x,
Yeah.
and then we divide?
Yeah. Plugged in 2 for x and 0.05 for dx.
Right, okay.
And then just divided, yeah. So again, like calculus-wise, very light, right? Kind of understand what's going on, but basically all you're doing is writing a tangent line and using it to make approximations. Yeah. Not so bad. Questions on 310? Okay. Let me write down the numbers I think I asked you to do. Okay. So 1, 3, 5, 7, 11, 17, 19, 25, 33, 35, and 37. Which again, that's not a ton, right? Most of these problems boil down to like writing the equation for tangent line and then plugging stuff into it, which is not so bad. The book's notation and everything like makes this seem really complicated. It's not that complicated. So I want to talk about the test for a moment here. I don't know if you noticed when I put the test review thing in here, but I have that in there. So, oops, not that one though. This guy should be down here, huh? So here it is. So I have 3 show questions. Show a derivative is equal to a specific expression. On these, algebraic simplification before differentiation could be quite useful. On you guys' exams, like the first couple of questions were all ones where the calculus should have been easy after you did some algebra. Most of us elected to do a lot of calculus and very little algebra there. So I'm just giving you a heads up that like that may not be a great plan on these ones.
One on might be a great plan.
Is to do a lot of calculus but very little algebra when you could do more algebra in the beginning and very little calculus.
Okay.
Maybe an easier route to get to the answer that I'm asking you to get to. And then I give you 3 examples of stuff that I think are pretty similar to what I would ask you. Specifically, one of them is going to call for logarithmic differentiation since that didn't appear on the last exam either.
Okay.
So I'll say specifically to use logarithmic differentiation to show something. So I gave you a couple of examples there that I think are pretty similar to what I would ask you guys to do. I have 2 story problems that are like 3.7 problems. One of them would be like a position velocity story problem. And then the other would be similar to some other one that I named. 2 3.9 related rate problems. I would call these both like pretty standard level related rate problems. And they don't have any tricks that you haven't seen before in the other related rate problems that you've done. So if you're like, you know what to do, you should be okay. And then I have 2 310 problems. Again, these will be kind of like multi-part story problems. And some of the parts will draw on some previous skills, such as implicit differentiation and the intermediate value theorem. So and I give you a couple of examples of things that I think would be pretty similar to what I would ask you to do. So I think that's the test format. So I gave you some specific stuff when it differed, I think, strongly from what you've seen in the text. If it didn't differ strongly from what you've seen in the text, I just gave you like some specific test or text problems that were things that we'd already kind of done.
So nothing from 3.8.
No. Because the only thing in 3.8 is like justify to write this equation because it's like, oh, the solution to this differential equation is this if it's of this form. It's like, well, I couldn't really find any evidence on the AP exam questions that I'd reviewed that ever came up, so I'm just like, eh. And one last thing for you guys as well. Cool? Everybody's okay?
Yeah.
2, 4, 6, 9. I mean, there's multi-parters,
Right.
but like 9 total questions. Is that okay? Feel reasonable? You have a good idea of what to review? Again, specifically like these ones that I put on here are like specific questions that I created myself. Like, make sure you do those and you feel good about them. Mia?
Where would you like use the IV?
Okay. So what does the intermediate value theorem allow you to say?
That like there's a value
Between these two x values, there should be another x that gives you this specific y value, right?
Yeah.
That's how you'd use it. Is it'd be like show that, if we had this data, and I'd say show that the battery voltage, equals 55. How would you use the intermediate value theorem to do that?
And then set has value.
And you said there exists value between
Partial credit. What didn't you do?
fine.
Nope. You don't need to find anything. The IVT never doesn't give you what that number is that gives you, doesn't give you the x that gives you that y. It just says that it has to be there. You need it continuous first. How do you know this is continuous? Elvis, you were saying it because it's twice differentiable, right? So that guarantees you that this function h of t is continuous. Then you can apply the intermediate value theorem the way Mia stated, that since like h of 4 is greater than 55 and h of 7 is less than 55, then there exists some c between 4 and 7 such that h of c is equal to 55. Like that's how you'd use it.
What lesson 2 and 3 or 2? 2 did we learn IVT?
Oof. It was a long time ago.
Yeah, I know.
It was way back in chapter 2 somewhere.
We need to say that. We need to state the intermediate value theorem for that. We'd also need to tell you why it's continuous.
To use the intermediate value, it's in section 2.5. Victoria, 2.5. So to use the intermediate value theorem, you need continuity. That's a requirement.
Right. So wait, do we have to prove continuity?
Yes,
Okay, so how would we do that again?
because it's differentiable.
Wait, how is it different?
It says so in the problem.
Oh, it's just different.
It was a snooze.
As a charge on a battery is discharged, the voltage of the battery is given by the twice differentiable function h.
Okay, so we would just state what it starts saying. Like,
Since h is twice differentiable, h is continuous.
Okay.
Boom,
And
done.
Pretty simple.
That's it. Or continuous over its domain anyways,
Okay.
right?
So we wouldn't have to plug anything in.
To use the intermediate value theorem?
Yeah.
No.
We would just say it's continuous because it's differentiated. And then you write like the let n equals 0.
Well, it's 55 in this case, right? Is the number that you're proving that there's an x somewhere in there that gives you the h of x equal 55. But yeah, that's all we're saying,
Okay.
right? You have two y coordinates that are bigger and smaller than 55. So there has to be an x in between those, that gave you those two y coordinates. That'll give you 55.
So we would do like 51 is less than 55 is less than 67.
Yeah, I would write it as like h of 7 less than 55 is less than h of 4.
Okay.
That makes it a little clearer when you say then there's, so there exists some c between 4 and 7 such that h of c is equal to 55, right? Yeah. But you could write it as 55 and 67, or 51 and 67. That wouldn't be wrong either. Or you could use 45 and 100, right? Like, that's fine too.
Show any work. We would just need to say.
No, there's no work to show for an IVT.
Oh, yeah.
And if you have a table of values like this, what can you do? What work can you show? You have no way of plugging values into a function.
Right. Okay.
Like, you don't know what the function, how to get the values for the function. It has to be coming from the table. There's nothing to do. They're just like, can I use the intermediate value theorem? Everything I need has to be here in the table. Right?
Yeah.
If it was something where it's like, it's a function, then you'd have to, and you've given like the equation for the function, then you might have to do a little bit of hunting. But usually it's not even that bad. Usually just use the endpoints of the function, or the endpoints for the domain, and it oftentimes will be enough. You know what I mean? But if all you have is a table to describe the function, then everything you need has got to be in that table. We'll stop here.